Today we're talking about single bonds, just one bond between atoms. By the end of this video, you should be able to connect two atoms together using a single bond and Lewis dot diagrams. Just as a refresher, I am phasing out of these timelines being in the lesson, and they will be in the comments below. If you're an educator, please check out the comments below if you are interested in seeing the timeline of the lessons and the Bloom's taxonomy that goes with them. For today, we're going to be talking about covalent bonds as a refresher from the previous lesson. If you haven't seen that lesson, go watch it. It's in the comments below. And then we're going to be moving on to single bonds. What are they? And how do we connect these Lewis dot diagrams together? Again, if you have no idea how to draw Lewis dot diagrams, go ahead and click on that link in the bottom where I teach you how to do that. First things first, before we can get to connecting atoms together, we need to remember the rule by which they all live and thrive. And that rule is called the octet rule. Every atom in the universe wants 8 electrons to turn that frown upside down. It needs 8 of them, or octet, hence oct like octopus, 8. It needs 8 electrons to be happy and satisfied inside. So if we're looking at the Lewis dot diagram for nitrogen and hydrogen on the screen, we can see that each atom is surrounded by its valence electron number. So nitrogen has 5 dots or 5 electrons for its valence, and hydrogen has 1. Now they're not happy like that. They only have 5 and 1, and they want 8. So this is a problem. We want the octet rule. They want to be completed, and they need to have 8 in order to be completed. So without adding in any more electrons to the nitrogen or to the hydrogen, without erasing any electrons, how could we make both of these atoms happy? How could we fulfill their destiny in that they all want an octet? Minus the case for hydrogen. Hydrogen's happy with 2, remember, from the shell model lessons and everything in the past. But otherwise, the atoms want 8. They want an octet to be happy. How could we fulfill nitrogen's happiness and hydrogen's happiness without intrinsically changing the valence number of electrons that are currently around them? The answer to this question is called covalent bonding. If you haven't learned about covalent bonding, watch my previous video. Covalent bonding is basically where there are different atoms sharing electrons to obtain this octet. So instead of magically getting electrons from the universe elsewhere, which would not really be possible, they have decided to overcome their lack of an octet by sharing, because sharing is caring. Isn't that sweet? So they all share so that all of them are fulfilled and happy, and they all have that octet. And the way that we show this with the Lewis dot diagrams, and the way that we can predict how a molecule will form and how it will share electrons, is based off of which dots are alone and therefore can be shared with the other alone electrons from a different atom. So if there are alone electrons on one atom and lonely electrons on another atom, those 2 lonely electrons can hook up and not be lonely anymore. Catch my drift? But on an atomic molecular level here, we're talking about the sharing of electrons. And again, as a reminder, they can share them equally, they can share them unequally. That's still covalent bonding. There's different flavors of covalent bonding. If they share them unequally, then we are talking about a polar bond. The electrons are being drawn to one atom over another. It's more electronegative. And if there is equal sharing, then we call that molecule overall nonpolar, because the electrons are buzzing about on both sides or all sides of the molecule equally. Therefore, there's not a more electron-dense region of the molecule. So let me show you as an example here. We've got 2 H's, each with a lonely electron, and O has 2 unpaired lonely electrons around it as well. So what we can do is literally play connect the dots. So that H's electron can hook up with the O's electron that's lonely, and the other H's electron can hook up with the other lonely O's electron. And when we do that, we get water, H2O. So notice that from hydrogen's perspective, it has 2 electrons now. And from the other hydrogen atom's perspective, it also has 2 electrons. And then if we look at oxygen, from oxygen's perspective, it has 8 electrons around it. So all the atoms involved here in the shenanigans are satisfied. Let's see if you get it. I want you to think about how many hydrogens would be required to bond with a carbon in order to fulfill each atom's octet. See if you get it. Pause the video here and think about it. Hopefully you're noticing that carbon itself has 4 valence electrons. In order to fulfill carbon's octet, in other words, having 8 electrons around it, we need atoms that can bring an electron each. A hydrogen has 1 electron to bring, conveniently. So since there are 4 valence electrons around carbon, we need 4 hydrogens, each bringing their own electron to the party. Now we can see that each hydrogen has 2 electrons from its perspective, and the carbon in the middle has 8 electrons from its perspective all around it, sharing these electrons together. Isn't that sweet? This is called methane. And yes, indeed, methane is cow farts. That big political thing about cows farting. Yes, methane. Let's jot down the steps for success in figuring out how to create and bond these atoms together using single bonds. Step 1. Draw the Lewis dot diagram for all the individual atoms involved first. First thing. So for NH3, you would draw an N and then 3 H's. That little 3 after the H is symbolizing that there are 3 individual H atoms. So step 1, draw Lewis dot diagrams for each atom present in the molecule. Step 2. Typically, you're going to put the least electronegative atom in the middle. So you're going to arrange these atoms you've now drawn previously and pick the least electronegative one. What's the least electronegative one? Check your periodic table. That's how you're going to know based off of the electronegative trend going across the periodic table towards fluorine, being the most electronegative atom on the periodic table. However, the exception to this rule is that hydrogen, even though it is very not electronegative, is usually going to end up on the outside of the molecule. And that's because hydrogen's special. Recall that it only needs 2 electrons. It doesn't actually need the 8 for the octet thing that all the other ones need. Hydrogen's satisfied with 2. It's easily pleased. Step 3. You're going to take note of wherever there are lonely electrons, wherever there are electrons that are not paired up around each atom. So of course the pair on top of N, you're not going to touch those. You're going to leave them alone. They already have a mate. They're satisfied. They got a date to go with to the dinner tonight. The other 3, however, are sad. They don't have a date yet, and that's where hydrogen comes in and goes, I'll help you out with that, buddy. So you're going to play connect the lonely dots. You're going to basically see wherever there is a dot that doesn't have a pair and connect the atoms together. Let me show you. So hydrogen can connect there, another hydrogen can connect there, and boom, we have 3 bonds. We have no more lonely electrons. They all have a date. All the lonely electrons, where do they all come from? They come from unbonded Lewis dot diagrams. And step 4. Now you want to clean up your mess because by now your paper probably looks like a flustercluck and you want to make sure that everything looks nice and tidy before you, of course, turn it in to your chemistry teacher. Duh. So you're going to clean it up by redrawing your molecule with lines instead of dots. So 2 electrons, when you pair them together, is equivalent to 1 line. 2 dots equals 1 line. So when you do this, essentially you're going to be replacing those dots with line. Again, notice that from nitrogen's perspective, it has 8 electrons total around it. From hydrogen's perspective, it has 2. From that hydrogen's perspective, it has 2. And from the final hydrogen's perspective, it has 2. All of the atoms here are satisfied. Everything is hunky-dory. We're going to clean this guy up and put lines in between instead. Notice that I kept the 2 dots that were bonded on top of nitrogen on top. You could still technically draw a straight line over nitrogen. I like to leave those alone. You want to keep those typically as themselves, as their pair on whatever's left over. In chemistry, we call those the lone pairs, or lone pair in this case. So nitrogen has a lone pair of electrons. Oxygen typically has 2 lone pairs of electrons on it. We usually keep those there. You don't want to get rid of them. You still want to show them so you can still see on the paper where are areas of more electronegativity. Let's put these steps into practice. Let's see what this molecule would look like all bonded together. Now remember the steps. Step 1 is to draw each individual atom's Lewis dot diagram. Let's do that. So first we've got one carbon atom and one hydrogen atom. There's kind of like an invisible one right here for each one of those, implied there by there just being the letter there. And then we have this 3 here, and that 3 applies directly to the chlorine that it's attached to. So that means that there are 3 chlorine atoms present in this molecule. In other words, we have a carbon, we have a hydrogen, and we have a Cl, Cl, Cl. We have 3 separate chlorine atoms. We need to draw the Lewis dot diagrams for each one of these. Looking at the periodic table, we see that carbon is 6. Its number is 6. It is also in the 4 column for valence if you're looking at the cheat sheet periodic table. Since carbon has a number of 6 electrons, its valence is 4, the number of electrons in the outermost shell. There are 2 on the inside shell, therefore there has to be 4 on the next shell up. So carbon has 4 valence electrons. 1, 2, 3, 4. Let's check out hydrogen. Hydrogen's number is 1, and it has 1 valence electron because that's all it's got. So since hydrogen's valence is 1, we're just going to put 1 dot next to it. How about chlorine? Chlorine's number on the periodic table is 17. You could do a shell model to figure out its valence, or we could use the shortcut. There's 1 valence here, 2 valence here, 3 valence here, 4 valence here, 5 here, 6 here, 7 here. So we know that chlorine has 7 valence electrons because it happens to be in this column. So around chlorine, let's play Ring Around the Atom. 1, 2, 3, 4, 5, 6, 7. So around chlorine, we have 3 lone pairs and 1 unbonded electron. I'm just going to make the other chlorines look the exact same. Excellent. Step 1 is complete. We have Lewis dot diagrams for each one of these atoms present in the molecule. Now we need to put the least electronegative atom in the middle, minus hydrogen because it's the exception. Between carbon and chlorine, carbon is the least electronegative between those two. So we're going to put carbon in the middle. All right, carbon goes right in the middle. We know we're going to have to pair up lonely electrons, and carbon has 4, so I might as well start arranging my other atoms around it in a way that the lonely electrons could get together. All right, I have now redrawn the entire setup with the least electronegative atom in the middle and the other surrounding it. Step 3 is to now connect the lonely atoms together. We're going to play connect the dots. So we see that there's a lonely dot here that can connect. We see there's a lonely dot here that can connect. There's one here that can connect. And last but not least, there's one there that connects. That looks awful. We need to redraw that before you hand it in to your chemistry teacher and drive him or her insane. Anywhere where we have connected the 2 electrons together on different atoms, we're going to just draw a straight line. Let's give it a go. We have C, H, Cl, Cl, Cl. Now that we've connected them together, don't forget those lone pairs on all of the chlorines. Those are still very important to show. So we want to still make sure that we carry over our lone pairs. Even though it's tedious, you want to keep them there. Now that would be our beautiful final answer, ladies and gentlemen. Voila. Let's end today's lesson with just a bit more practice. Let's draw the Lewis dot diagram for the following 2 molecules, and be sure to keep any lone pairs at the very end. Step 1 for HCl. We have 1 H atom and 1 Cl atom present. We need to draw a Lewis dot diagram for H and a Lewis dot diagram for Cl. What we learned previously is that H has 1 valence electron, and we learned that Cl has 7. 1, 2, 3, 4, 5, 6, 7. Now that we've got the Lewis dot diagrams for each individual atom drawn, we're going to put the least electronegative one in the middle. In this case, there isn't really a middle because there's 2. So step 3 would now be just connecting the lonely electrons. There's 1 lonely one there, 1 lonely one there. So all we need to do now is just clean up the molecule. Wherever there is a connection, we're going to draw a single line. So H line Cl, Don't forget to carry down those lone pairs around chlorine, and that is your final answer for the molecule of hydrochloric acid, HCl. Let's give H2S a try. In H2S, we have 2 H atoms and 1 S atom, 1 sulfur. So we're going to write H, H, S. Hydrogen has 1 valence electron, just as we've done before. We need to figure out sulfur though. So let's go back to our periodic table to do so. There's sulfur in placeholder number 16. Let's use our shortcut to figure out how many valence electrons sulfur has. This column has 1, 2, skip the middle, 3, 4, 5, and 6 in this final column. So 6 here, sulfur would have 6 valence electrons. Let's go back and put those in around our sulfur. 1, 2, 3, 4, 5, 6. Sulfur has 2 lone pairs and 2 unpaired electrons. We already have the most electronegative atom in the middle, that would be sulfur, and the hydrogens are on the outside. So let's jump to step 3 and connect the lonely electrons together. We have 1 lonely one there, another lonely one there, and 1 lonely one there, and another lonely one there. Let's redraw this molecule, make it look super pretty. S, line, H, line, H. Don't forget these 2 lone pairs. Bring those down with you around the sulfur. And that is our final answer. Now, not all molecules are just going to have single bonds. Sometimes you end up having to draw double and triple bonds. Please watch my next video to learn how to do that. I hope this was helpful for you. Show a duck some love. And be sure to hit that like button on this video and subscribe to my channel. See you later.
No ducks, no glory.